Distributed localization of a group of underwater robots. This is a common work with Aymeric Bethencourt, who made his PhD on this topic at ENSTA Bretagne. All what will be presented here is based on contractor programming. So I will first introduce what is a contractor. Consider here so R2. So R2, here you have X1, there you have X2, and we consider a set. So it can be a set or an equation, maybe an equation. For instance, the equation will be f of x equals 0, but it can be any other set. Consider now a box. So a box, I represent here a box. I draw it green. And a contractor is an operator which associates to a box. So here's a green box, another box. Here, I will paint it, for instance, this color. And here I will have this box will be the contracted box, so C of x. So C is a contractor. And here in blue, in green, you have the box X. So the contractor C will be an operator which associates a box to a box X, another box. And we'll have to follow some property. So the first property is a contraction property. I mean, C of X should be included in X. So C of X is smaller with respect to the inclusion. So here, take care, it is inclusion, whereas here you have the contractor C. And the other property means that if S is this equation, is a set corresponding to this equation. So for instance, S is a set of all x such that f of x equal to 0. Then the other property we should have is the intersection between x and S is the same as C of x intersected by S. So here in the picture it is the case, since as you can see, the intersection between x and the set S corresponds to this part of the equation, and we can see that it is the same for the contracted box. So, with other words, it means that if one point, say for instance this point, is inside X before, so a solution, a point which belongs to the solution set. If one point belongs to X, then it should also belong to the contracted box. I mean that the contractor should not remove any solution. So in this case, we'll say that the contractor C, so if I have this, I will say that C is a contractor. Associated to the set S. Okay, so this is the definition of contractor. So here I have defined in a contractor from the set of boxes is an operator from the set of all boxes to a set of all boxes which satisfy the contractance property and the consistence property as explained before. How can I build a contractor for equations? Most of the time I have to use interval analysis. I will show in the very simple example how it works. The equation I consider here is x1 plus x2 equal to x3. So if we prefer, here I have my function sorry. I have here my equation f of x. So x corresponds to x3 minus x1 minus x2. Since this f of x equal to 0 is equivalent to say that x3 equal to x1 plus x2. So how can I define a contractor for this? So I will have assume that I know that xa belongs to an interval xi. So it is the case for I belongs to 1, 2, or 3. So for this simple equation, I can write that x3, for instance, belongs to what? So first, I know that it belongs to x3, but it also belongs, thanks to this equation, it also belongs to x1 plus x2. x1 plus x2. Okay. Now, because of this equation, I can also rewrite this equation as follows. I can write that x1 is equal to x3 minus x2. So I can write now that x1 belongs to x1, so I already know this, but it also belongs to, thanks to this equation, it also belongs to the interval x3 minus the interval x2. And this can be computed, so I have to use interval arithmetic rules to compute this and this. So I have explained now how I contract x3 and x1, and now I use the last one. So also from this equation, I know that x2 is equal to x3 minus x1. So here I can write x2 belongs to x2, but it also belongs to x3 minus x1. Okay, so here I have a new interval. So this corresponds to an interval. This corresponds to an interval, and this one also to an interval. So my contractor will, from x1, from x2 and x3, x2 and x3, so from these three intervals, I am able to compute these three intervals. So, if you prefer, this is the box X, which belongs I are 3, so the set of boxes or of intervals of S3, and this corresponds to the contraction of X. So, in this case, I will satisfy the property which is explained here. I mean, the contracted box is smaller than the previous one with respect to the inclusion, and I do not lose any x1, x2, x3, which satisfies x3 equal to x1 plus x2. Moreover, in this case, I have the optimal contractor. I mean that I have plenty of possible contractors, but this one is the smallest one with respect to the inclusion. Okay, now I will introduce interval trajectories. For us, a trajectory is a function from R to Rn. Here is an example of trajectory. If I want to represent a trajectory, here I will have the time t, so most of the time it will be the time t. For the y-axis, I will have Rn, and this is a trajectory. Okay. What is an interval trajectory? To define an interval, I need first a partial order set. And to be more specific, I need a lattice. What is a lattice? A lattice is something we use in order theory, is a partially ordered set for which two elements have a supremum and an infimum. We'll try to explain it maybe more in a more simple way. So if I have two elements, when I have a lattice, if I have two elements, say A and B, I will be able to define the infimum, A and B, and the supremum, A and B. Let me maybe explain you what this means. I will take an example, for instance, R2. Here I have R2, and in R2, A could be here, and B could be here. If I take C here, C can be considered as greater than B because all components for C are larger than B. So I can say that C is larger than B. C is also larger than A. But we cannot compare with this order. For instance, we cannot order B and A. So I can say that A is smaller than C. I can say that B is smaller than C also, but I cannot say that A smaller than B or B smaller than A. I cannot write this. So I have a partial order. So I have a lot of points such as C that are larger than B and larger than A. But one is smaller. So there is a smaller element which is among all elements that are larger than B and A, there is a smaller element, and it will be here. So for instance, this point is larger than A and then B, but it is the smallest one. So it is a supremum, and this one will be called A supremum between A and B. Again, D here is smaller than A and then B, but there is an element which is the largest minimum of A and B, and this one will be called A AB like this. So if you prefer, in a lattice, R2 is a lattice. So here, of course, I am working in R2, but I can define the smallest box which enclose A and B, like this one. And if I have any set, for instance, say any set such as this set, for instance, with this set, I can always define the envelope, the interval envelope of a set. Okay. Oh, I have an example of lattice, but the set of trajectories is also a lattice. So let me consider, for instance, what we call an interval trajectory. I will try to represent one here. I will have this unknown trajectory can be bracketed between, sorry, between two trajectories, this one, for instance, and this one. Hop. And this corresponds to, so it will be, this part corresponds, for instance, to F plus. This trajectory corresponds to F minus. And this trajectory, which is most of the time the unknown trajectory, which corresponds to F. So in this case, I will be able to write that F belongs to the interval F minus and F plus. Okay. So if I have two interval trajectory F and G, I can compare them. So I will say that F is smaller than J if for all components, if for all t, I have f I of t smaller than j I of t. I can define the, as explained before, the infimum and the supremum, and the set of trajectories is a lattice. And I can define intervals of trajectories, and these interval trajectories are tubes. So I will be able to define the intersection, the union, and so on. So let me just illustrate here. Consider that I have two interval trajectories or two tubes, which is equivalent, x and y. The intersection between these two tubes is this one. Okay, the green part corresponds to the intersection between x and y. The union, I will draw now the union, for instance, yellow, it will be this, this, and also this. So this corresponds to the union. If I want to evaluate over an interval with respect to a tube. So if I consider this interval, I will take all possible images and I will define the image of an interval at the smallest interval, which contains all feasible evaluation. If you want, a tube will correspond to interval or set membership counterpart of what we call a random signal. So most of the time, a tube encloses a trajectory which is not known. An example of interval trajectory is this. So I have a function cos and sine, and I add an interval, and I have here f of t corresponds to an interval trajectory or a tube. I will be able to define contractors thanks to tube arithmetic. So what is tube arithmetic? I consider two, uh, two tubes x and y, and I will be able to define the sum or the composition of so on of two tubes as by taking all the smallest interval or the smallest tube which enclose all feasible uh, result of signals x and y when I apply the corresponding operation. So let me consider, for instance, an example. If I take here, if I take sorry, x of t, so it is a signal or a trajectory which belongs to x minus of t, x plus of t. Y of t belongs to the tube y minus y plus of t. So here, x minus y minus x plus y plus corresponds to trajectory, but here I have a tube. Then I will define x of t plus y of t, but I take here the tube. So if you prefer, this corresponds to the tube x of t, and this one corresponds to y of t. So this will be equal to the tube x minus of t plus y minus of t, and here x plus of t plus y plus of t. Okay, in the same manner, um, I will be able to write that the integral between, let's say, 0 and t of x of 2 d2 will correspond to the following tube. Integral between 0 and t of x minus of tau d2, integral of between 0 and t of x plus of tau d2. Okay, so the semantic is the following. if I have x of t, which belongs to the tube x of t, then if I take this definition, I will have the integral between 0 and t of x tau tau belongs to the integral between 0 and t of x of tau tau if I apply this definition. And I will have the same kind of rules if for the addition and so on. So if I apply this way of thinking, this reasoning, I will be able to define what we call the interval arithmetic of trajectories, or what we call the tube arithmetic. I will be able to define the shift onto the right or to the left, and this is the kind of operation I can apply: addition, the shift, the composition, the integral, and so on. The role of tube arithmetic, similar to interval arithmetic that we have proposed before for real numbers, the role of tube arithmetic is to build contractors. I will take a very simple example in order to explain how to build a contractor for tubes. The example I consider is the following. I have x dot of t, so it is an unknown trajectory, which is equal to x of t plus 1 multiplied by u of t. I know tubes for x, x dot, and u. So it means that I know that the uncertain trajectory x of t belongs to this tube. I know that x dot of t also belongs to this tube. And also for u of t belongs to the tube u of t, to the interval trajectory u of t. So in order to build the contractor, first I will decompose into a primitive equation. So it is, in fact, this corresponds to my equation, and I want to contract all tubes for x, x dot, and u without removing a simple trajectory, which could satisfy this equation. So in order to decompose this equation, I will add intermediate trajectories. So I will define a of t, which is equal to x of t plus 1. So if you want, this corresponds to a of t. I will define y of t, which corresponds to the product of a of t and u of t. And I will define the last equation, which says that x of t corresponds to x of 0 plus integral between 0 and t of y of tau d tau. So it means that here I have a, here I have y of t, And since x dot corresponds to y, it means that x can be obtained using this integral formula. Now I will be able to use the tube arithmetic to define the tube arithmetic to contract with respect to this equation. So let me first consider, say, this first equation. So from this equation, I will be able to write to contract. So A of t will be contracted as follows. It belongs to A of t, the previous one. So the new A contracted tube corresponds to this one, but it is also the intersection with the shift of x of t plus 1. So this one is obtained by shifting by 1 the tube for x. But this equation, so this can be rewritten if I isolate x. I can also rewrite this one and to say that x of t is equal to a of t minus 1. Okay, so it is always the same method. I isolate one of the variable and then I apply interval arithmetic. So here, for this equation, I have x of t will be contracted as follows. X of t intersected by a of t minus 1. So I have the contractor corresponding to this equation. So of course, for the initialization, I will have to for the initialization of a, since it is a new variable, I will have to write that a of t corresponds to minus infinity plus infinity, and then it will be contracted using, for instance, this first contractor. Okay, I consider now the second equation. Let's say this one. Uh, if I apply this equation, I will obtain that y of t uh, is equal to y of t intersected by the product of a of t multiplied by u of t. But I have another way to, I will isolate now a. For instance, I obtain that a of t is equal to y of t divided by u of t. And thanks to this, I will be able to write that a of t is contracted by a of t intersected by y of t divided by u of t. But I can also write isolate u. So u of t is equal to y of t divided by a of t. And then here I will have u of t is contracted as follows. U of t intersected by y of t divided by a of t. And for the last equation, I will have the following contraction. X of t will be equal to x of 0, oh, maybe, sorry, a of t, intersected by x of 0 plus the integral between 0 and t of the tube y of 2 d2. So, if I apply all this equation, especially up to the fixed point, so I will apply several times, but of course I will have to initialize a and the other variable y. Y of t should also be initialized to minus infinity plus infinity. If I apply all this equation several times up to the fixed point, then I will obtain a contractor for this equation. Okay, so this is what I wanted to explain here, that tube arithmetics is a good way to build contractors. I have a trajectory, x, and I know that it belongs to a tube, but I also know that x is periodic with a period equal to 1. So I can write with the following constraint: x of t is equal to x of t plus 1. What I want now is to contract the tube. Uh, of course, as I explained before, I have to decompose into two equations by introducing a new variable, a new trajectory, here a. I will build a contractor for the first equation, but also for the second equation, as before. And in this case, I obtain this contractor. So the first two equations corresponds to the fact that a corresponds to a of t plus 1, and the two last equation corresponds to the fact that the trajectory x is equal to the trajectory a. So if I apply here the tube arithmetic, so mainly here the shift of plus 1 and minus 1, I will contract, and I will illustrate now graphically how it works inside the machine. So I know that x is unknown, but I only know that x is inside this tube. So x cannot be like this because x is monotonic. So here I don't know exactly what is 1, but say assume that 1 is like this, for instance, this corresponds to 1. Then x could be something like this. Or let's say this one. Good. This is periodic, but I am outside the tube here. So it cannot be this. I will try now to show what it can be. So I know that I am inside this tube, and I will apply the first contractor. So the first contractor corresponds to this one. And then I will apply this one. I have to explain also that inside the machine, a tube corresponds to a vector of intervals, to a list of intervals. And that's why here I have plenty of thin rectangles, slice, a lot of slices. Of course, all slices are represented in the machine by floating point numbers. So first, I will take this tube and I will shift it to the right. And if I switch it to the right, I obtain the dark gray tube. And I will have to intersect it with the previous tube as explained here. So here I am now doing this one. So I will intersect and I obtain this. And I know that my trajectory X is inside this tube. Now I do it, I apply the second contractor. So I switch left. And of course, when I switch left, like this, of 1, so this corresponds to 1, this corresponds to 1, all what appears corresponds to minus infinity plus infinity, because in the machine I don't know what I have beyond this the maximum t and the minimum for t. Okay, so now I switch left, I do the intersection. And then I switch right, and I do the intersection, I switch left, and so on. And at the end, I will converge to this tube. So quite quickly, I converge to this tube. And the only thing I can say is that the tube for X is inside the dark gray tube. So here, light gray corresponds to the initial tube, and I was able to contract the light gray tube to the dark gray one. So if you want, here I have the tube X, a dark gray, I have the contraction of the tube X. Sorry. So it means that the tube I want to find, the trajectory I want to find, is this one. Time-space estimation. So the notion of time-space estimation is important in the context of underwater robotics, since the travel time of the sound inside the water cannot be neglected. So a classical estimation problem can be expressed as follows. First, you have a state equation where x is a state, u is the input, which is assumed to be known, and you have an equation, or this kind of equation. Of course, I should have the uncertainty, but just to illustrate the principle, here I just have written an equation where that x of t should satisfy. So this equation is called the space constraint, since I have an equation which depends on the state at time t only. So if I want to, I will draw what happened. I have here the time t. Here I will write x, the state at time t. So I can go from state at time x, for instance, at time t prime, by integrating the differential equation x dot equal f of x and u. Okay. But I will have some exteroceptive measurements, or some measurements. So here I will write an equation j of x t, which depends of t, because the measurements is included inside g, okay, which is equal to 0. But also for this one, j of x prime t prime prime equals 0. It is a graphical representation of a state estimation, classical state estimation problem. Here is an example. You have here the state equation which is given here, and here you have a measurement equation at time t, which is equal, which is equal to 5, whereas here you have an equation for t prime equal to 7. Okay. Now, what happened is you have another type of problem that we will consider here. It is, you have a robot or several robots, but here one robot, for instance, and I have an equation which links the state at time t, but also with the state at time t prime. So what is the difference? Graphically, I represent like this. I have here an equation which link these two states. So it is not like this one, like before. You have here j of x and t, x at time t prime, t and t prime, and this is equal to 0. So now you do not have, as before, you had a separate equation here and here. Now you have an equation which makes the state at time t and the state at time t prime. Okay, again, this equation could also have been written y equal j of x and t, but here I decided to write an equation like this just for simplification, but it's the same. Okay, it's the same. So it is what we call a time-space constraint, because you mix the time and the space inside the equation. It's for different time and different state. So an example of time-space constraints is when you have ultrasonic underwater robot. So it is only one robot, but which go very fast. This robot goes very fast. So if I draw this, I will have this one, this picture. I have the robot here at time t, and at time t, it emits some kind of waves like this. I represent like this wave. Okay, and this wave move with respect to direction like this. Okay, but this robot goes very fast, faster than the sound. It is here at time t prime. So, of course, it will receive the sound this. That has been emitted at time t. And in this context, it will receive the sound at time t prime. And here the robot was, the state was x of t, whereas here it is x of t prime. So I can write an equation which makes this and this. And this equation is given here. So it says that some kind of Minkowski distance, which is equal to 0. So here c is the celerity of the sound inside the water. So this is a state space constraint. Consider here a very simple example, which is not immediately related to robotics, but which involves a state space constraint. It is a mass spring problem. You have a mass with a mass spring problem, which is described by this equation. So if I can write here, I have the mass. Here I will have the spring, and the position of the spring is x. Position of the spring is x. If I define the state x like this, equal to x1, x2, then my equation can be written into this form. So this form is as x equal to f of x. Okay, x dot equal to f of x. It is represented here. I have my spring. The distance between the left wall and the right wall is L. The sound is emitted at time t1 and I receive it at time t2. So in this context, the time of the sound emitted here and received here will correspond to t2 minus t1. Then I get this, I will get this equation. So here it is the evolution equation, and here it is the time-space constraint, which links the state at time t1 and the state at time t2. Okay, so here is a link between the two. Okay. Then I apply the contraction. So my measurements make me possible to contract at different time. Here time t1 and t2. Here on the left column it corresponds to x. So here to x. So here you have x. Here x again. And on the right it will be x dot. X dot. Okay. So because of the measurements, I will have some contraction which presented on the left by black, and then I will propagate, and slowly up to the fixed point, I will be able to get an enclosure envelope for X, but also for X dot. Swarm localization. I will consider here the problem of localization of underwater robots, taking into account the time of the sound inside the water. So I will consider different robots, R1, RN, and I will now explain what happened. I have one robot here. It is, let's say, the robot number one, and it is not an ultrasonic robot. I mean, the robot moves quite slowly compared to the sound. It emits at time A. So A now is time, A, a sound. The sound is represented like this, with the sound. And so this is the sound moving. And here you have another robot. Up, maybe like this. And this is a robot number two. And at time B, it receives the sound. So at time, let's say A, the robot 1 was here. He has moved like this. This is the trajectory of the robot and will continue to move like this with respect to this direction. The robot number 1 is also moving like this, and at time B, R1 is here. So we can see in this picture that we have a state time-space equation which links the state of the robot 1 with the robot 2, but at different times A and B. Okay, so it is a time-space constraint. Oh, what is a ping? A ping corresponds to one measurement. It will link what the state of the robot I and J at different times A and B. So it corresponds to the observation equation, to the measurement equation. So I is a emitting robot, and G corresponds to the receiver, the receiving robot. I have here a picture which is similar to the previous one, but here in the x-axis I have represented the state, whereas here it is the time t. So at time A, my robot I, so robot I, is emitting, but A is smaller than B, and later at time B, the robot RJ G received. So this, what I have here, this corresponds to what I have called a ping. Okay. So for each robot, I have a state equation, but I have also a time-space equation, which links the state of X at time of the robot number I and G, but at different time A and B. So here it is the the big number k. J corresponds to the Minkowski distance between the position at time x1 and x2. So it corresponds to this function, which depends on x and A and B. Okay. Now the clock are uncertain. So I do not know exactly the time A and B, the absolute time, but I have I can read with an error the time. So A tilde corresponds to the time measured by the robot number I at time A, and this function, the clock function h for I and G is unknown, is not perfectly known. So I will represent them by a tube. Okay. Now another problem is that the drift of the clocks is unbounded. So, excuse me, is bounded, but it is not exactly known. So I have a state equation for each of my robots. The input is known to belong inside an interval, Ui. I have my measurement equation, my time-space equation, which corresponds to a ping or to a measurement. I can read my clock for the robot number I and G, but I also, this equation will tell me that the derivative of h is 1, more or less, a small error, and this error is bounded. Why I say that here, that the drift of the clock is bounded. So let me come back to my function h. I will try to represent how it is represented here. So my function h, I have here, up, I have here my time, let's say t, and my function h is something like this. So in ideal situation, when I have no drift, my function h is like this. Okay, h of now, due to some uncertainty, my function h is like this. The derivatives is almost equal to 1, more or less, an error. So at time A, my clock will give me A tilde, and this is for one robot. For another robot, I will have something like this. It corresponds to the clock of the robot J, as here it was for A, and at time B, I will measure B tilde, as explained here. So I just say here that the derivative of the clock is almost equal to 1. I will now illustrate with some videos how the propagation works. Because now, as we can see, H and X are uncertain. They will be represented by tubes, and I will perform a propagation on each of these equations, and these equations involve uncertain trajectory, which are represented by tubes. Each equation will correspond to a contractor, and I will be able to contract each tube by taking account each equation, and this has to be done up to the fixed point. So I will have contraction and contraction, and I will stop as soon I have no significant contraction. In this simulation, I have 6 robots. Some robots at the top are moving inside with respect to a circle, and where at the top of the water, they are able to contract their position thanks to the GPS. They are able to communicate with pings. We can see the pings by red segments. They can, when they are near one to another, they are able to communicate their position, to measure the distance, and we can see that some robots are able to have, were able to contract the position so these robots are able to contract their position without using the GPS, but only by measuring some distances between some other robot. So you have some small communication between the robot, and everything is performed in a distributed way. So there is no centralized algorithm. Each robot is able to perform his own contraction by his own algorithm. In this case, I have no drift between the clocks, just a small illustration. I consider now another example on the plane where the clocks are not exactly known, there is a drift. I also consider the sound, the fact that the sound takes time to go from one robot to another robot. And the speed of the sound is represented by the circle. Sometimes the robots are able to communicate by pings, here as red segments, where they are near one to another. And in this case, sometimes they are able to perform their localization to improve the box. So I do not represent the tubes here, but if you draw all these boxes with respect to time, you will obtain a tube. Uh, as we can see, the robots are on the left are able to localize thanks to some GPS, for instance, and on the right they were able to localize with respect to the robot they see on the left. Okay, so now a last simulation with something like 500 robots are represented here. Again, the drift of the clocks are taken into account. Here, the segments correspond to the ping. We have different group of robots, but we can imagine that they are all the same. We can see the boxes, which corresponds to the position, the estimated position of the robot. And when one robot, and here we can represent the communication of the robots, but also the fact that the sound takes time to move from one robot to another robot. The robots at the surface are able to localize thanks to the GPS, and this information is communicated downward to the other robots. Again, everything is computed in a distributed manner. All this software have been made by Emeric Bethencourt during his PhD. And you can find here some references, papers of Emmerich in different journals, but also his PhD thesis on interval analysis for swarm localization.